Hi everyone, welcome to the channel. Today we are going to discuss about system design for notification system. Basically, how do we deliver the right message through right channel at the right time? Let's dig in. Before jumping into high-level design, let's clarify requirements. Let's finalize the scope of the requirements first, so we know exactly what we are designing. It's always good to ensure with the interviewer about requirements first, before jumping into any assumptions from our end. Let's discuss about functional requirements. Our first functional requirement is multi-channel support. In simple terms, multi-channel support means your system can send notifications to users through different mediums like push notifications. These are lightweight messages sent directly to a user's device, like a phone or browser, even when the app isn't open. Example, you get a push notification from a food delivery app. Your order is out of delivery. It's real-time and perfect for time-sensitive updates. Second, SMS notifications. Here's a best for protocol or offline friendly communication, especially when the internet is spotty. For example, your bank sends you an SMS alert, $500 withdrawn from your account ending in 1234. Next, email notification. These are ideal for detailed, non-urgent messages like invoices, account activity, or newsletters. For example, an e-commerce app sent you an email. Thanks for your purchase. Here's your order summary. Now our next functional requirement is deduplication. Imagine this. A user triggers multiple actions at once. Maybe they click submit a few times, or multiple services resist the same event. Without deduplication, they could get 5 notifications for the same thing. For example, you are tagged in a photo and get 3 identical push notifications. That's annoying and it feels like spam. Next is rate limiting. A crucial control to avoid overwhelming your users. Let's say a user performs a burst of activity, adds 20 tagged items to a wish list in 1 minute. Do you really want to send them 20 emails or push alerts? Probably not. For example, you like 15 posts on Instagram, but only get 1 notification. You like 15 posts today. And finally, we have delivery tracking and logging. One of the most underrated but essential features. Once a notification is sent, you need to answer. Was it delivered? Was it read? Did it fail? Why? This is important not just for matches, but for debugging, auditing, and retail logic. Example, you signed a password resent email. The user says they never got it. With delivery tracking, you can see if the email is sent, is it delivered, is it bounced, etc. So this is our functional requirements for today. And now let's discuss about non-functional requirements. Scalability. A good notification system must scale from thousands to millions of users without breaking or scaling slowing down. Example, Black Friday sales goes live. Your system needs to send millions of push and email alerts within minutes. Next up, reliability. Users expect the notification to actually arrive. If a system says it sent a message, it better have sent it. For example, a user doesn't get a password reset email. They are locked out and frustrated. Now, let's talk about fault tolerance. What happens if a part of your system fails? Say your SMS provider goes down. Your system should degrade gracefully, not crash entirely. For example, your primary SMS gateway fails, a fault-tolerant system would retry with a second provider, log the failure, optionally send a fallback email or push notification. And finally, latency, which is very critical. Some notifications are time-sensitive. If they arrive late, they are useless. For example, you get a notification that your delivery is arriving 2 minutes after the driver already left. That's not just annoying, but it's a broken experience. So latency is a very important part of the notification system. And these are the functional and non-functional requirements which we are going to cover in today's video. Now, let's walk through high-level design. Before sending notification, we need to collect data. Our main focus is notification system, so in this case, we will discuss about collecting data at very high level. We will take one of the real-life example here to collect data. A user just bought clothes from an e-commerce website. We want to send them an invoice via email or SMS, depending on their device. So let's break down how this works. So the flow starts when a user places an order. Maybe their phone, table, tablet, or desktop. The request hits the load balancer, and the load balancer will route this request to an API server. Now, before going through the next step, I want to give a very high-level idea about algorithms which are being used by load balancer. Load balancer has many different types of algorithm for routing, and you decide the algorithm based on your needs as well as your performance requirement. So when it comes to routing, we can have any different type of algorithm. The most common is round robin, where requests are distributed evenly in rotation, server A, then B, then C, and so on. Another is list connection, which sends traffic to the server with the fewest active connections, making it great for long-lived sessions. You can also use IP hashing, which routes users based on their IP address, helpful if you want a user to always hit the same server for session consistency. Choose the right algorithm depends on your app's traffic pattern and performance need. Now, we will go to the next, which is like once the request is hit to load balancer, it will send request to API servers. And then API server will save data into the database. In this case, we will be saving certain type of data, especially which we need for notification. We will save user ID, user's email address, their phone number, and if they are coming from any device, then we will be also saving device ID. These are just basic user information. In parallel, for the invoices, we also need to say what they bought, etc., or the pricing of the clothing, etc. So this is how we are going to collect data for users. And this was just one of the real-time example for a reference. You can also use any other real-time example where user has to save their data and we have to send them notification via push notification. So this is our step 1, how we collect the data. Now, step 2 is the main step, which is notification system. How do we send notification to users? Let's get started with step 2. Once we have data into database, we put the notification request into a message queue, like Kafka, RabbitMQ, or AWS SQS. Why a queue? It decouples notification creation from delivery. It helps us buffer traffic spikes. It makes the system more resilient and scalable. From here, a service called the notification processor picks up messages from the queue. The notification processor is the brain of the system. It handles 3 critical responsibilities before sending anything out. Deduplication. First, it checks for deduplication. We don't want to send the same notification twice. It checks recent history or uses a unique ID or fingerprint for each notification event. If the message is a duplicate, it's dropped right here, saving bandwidth and improving UX. It also checks rate limiting. For example, don't send more than 3 SMS messages per user per hour or 1 push per minute. This prevents spam and avoids overwhelming users. If the limit is exceeded, the message can be deferred, bashed, or discarded based on policy. And last, if the message passes both checks for deduplication and rate limiting, it gets forwarded to the channel dispatcher. The channel dispatcher is responsible for deciding which channel to use, email, SMS, or push, based on the notification type and user preferences. For example, for invoices, it may prefer email. For OTPs, it will prioritize SMS. For promo offers, push might be best. Once the channel is selected, the dispatcher sends the message to the appropriate channel adapter. This is where the system integrates with external services. For push notification, the adapter sends to Apple Push Notification Service. Email it routes to providers like SendGrid, Amazon SES, or Mailgun. This adapter sets check the provider-specific logic, making it easier to swap vendors or add failover logic later. Most of the message list adapter is in the hands of the provider and ultimately gets delivered to the user's device inbox or SMS inbox. For example, if it is push notification, then the message will be delivered to the device, which might be your Apple phone or Android. If it's SMS, then also again it will be delivered as a SMS message by Twilio or any other provider which we are using it. And if it's an inbox, if it's an email, then it will be delivered to your inbox using email provider. So this is how adapter will send push notification or send notification via push notification, SMS or email. On Firebase Cloud Messaging. For SMS, it might use Twilio, Nexmo or AWS SNS. Now comes one of the most important but often overlooked parts, tracking and logging. Once the notification is sent, we need to know, was it delivered, was it open or clicked, did it fail? Here is where the analytics service comes into play. It collects events from the adapter or provider callbacks and stores them in a central login database or analytical service. So, after it delivered, we will call analytics service here. An analytics service will save the tracking and logging data into database. Let's recap the key components. Queue to buffer and decouple. Notification processor for deduplication and retransmitting. Channel dispatcher to choose the right channel. Adapters to integrate with external services. User delivery through SMS, email or push. Notification. An analytics service to track delivery and engagement. This design is modular, scalable and extensible, making it easy to plug in new channels or upload logic without rewriting the entire system. This is high-level yet realistic architecture for a production-ready notification system. It handles real-world concerns like deduplication, retransmitting, and analytics tracking, while staying modular and scalable. Okay, now that we have covered the high-level design of our notification system, let's get a little naughty. First, we are diving into two features that are mission-critical if you don't want to spam your users into oblivion: deduplication and retransmitting. And guess who is our superhero here? Yep, it's Redis. Our in-memory key value stored does insanely fast. Let's start with deduplication. Think of Redis like a digital doorman. Before any notification enters the body, Redis checks, "Hey, have I seen you in the last 5 minutes?" Here is how it works. When the notification processor receives a message, we generate a deduplication key, maybe a hash of user ID plus notification type plus object ID. For example, user123_order_5678. Before sending the message to the dispatcher, we ask Redis, "Is this key already in the store?" If not, Redis adds the key with the TTL, say 5 to 10 minutes, and we continue. If it exists, that means we have already sent this recently, so we discard it. I suggest 5 to 10 minutes TTL, depending on how often a specific type of event can occur. Use 5 minutes for OTPs or confirmations. Use 10 minutes for user actions like order placed or status updates. Think of it like a short-term memory to avoid déjà vu notifications. Next up, rate limiting. We use Redis again here to track how many messages we have sent to each user in a certain time window. Here is one common way to do it: the fixed window counter. We define a row, max 3 SMS per user per hour. In Redis, we create a key like rate limit: SMS: user ID: timestamp. The key means SMSs for user 1234 during 2 to 3 p.m. on X date. When we send an SMS, we increment the counter for that key in Redis. Set a TTL of 1 hour. If the count exceeds the threshold, we skip sending and maybe log a Q8 for retry. You can also implement sliding window using sort2save timestamps, token bucket or leaky bucket for smoother traffic control. Use different limits for different channels. For SMS, it is more expensive, tighter limits. For push, cheaper and more lenient. And for email, use moderate one. And yes, make those context per user, per channel or per notification type if needed. So in summary, deduplication is Redis asking, "Did I already let this guy into the club recently?" Rate limiting is Redis saying, "Whoa, slow down. You have already messaged Tate's user 3 times today. Let them breathe." And both works because Redis is fast, lightweight, has built-in details, support atomic operations. Put simply, is perfect for real-time systems like notifications. Now let's look into reliability and fault tolerance. We need to look into what if something goes wrong. The SMS provider is down, the email bounces, or push fails silently. That's where today's topic come in: pretest strategies, letter queues, multi-channel fallback system. Let's bulletproof our notification pipeline. First, retest strategies. Let's say we try to send push notification via SMS, FCM, or APN, and it times out. Should we just give up? Of course not. We use retest strategies to give messages another shot. There are two main approaches. First, exponential backoff, bit jitter. Instead of retrying instantly and slamming the provider, we space out retries like this. First try every 2 seconds, second try 4 seconds, third try 8 seconds plus random jitter. Jitter adds randomness to our retry storms when thousands of failures happen at once. A second approach is retry queues. Here, I would like to apply retry queues. We will add separate queue for each type of notification. So for APN or FCM, there will be a separate queue which will be just handling only push notification related data. For Twilio, we will add another queue which will have data only related to SMS notification. And same thing, we will add third queue which will be handling only email related notification. So it will be email queue. And each queue will have its own retry mechanism. Each retry attempt can be sent to a dedicated retry queue. We will have retry every after a few milliseconds. Each of these has its own delay logic. If the final retry fails, we hand the message over to DLQ. The notification preview. When all retry attempts fail, the message goes here at DLQ. Why? So it doesn't get lost, so we can debug or manually inspect it, so it doesn't block or crash the main system. For example, if 3 retries to Twilio fails, the SMS notification is moved to the DLQ with metadata like error code, timestamp, notification type, user ID, etc. You can monitor the DLQ with alerts like 100 millisecond, or you can set that 100 SMS failures in last hour, or even with an admin dashboard for minor send or reprocessing. Now let's look into multi-channel support with multi-channel fallback system. So here is where things get smart. Let's say push notification fails. What next? A solid system doesn't give up. It falls back to another channel. So example flow for this will be try push my FCM. If FCM fails, maybe device is offline or token is invalid, send SMS. If SMS bounces or number is invalid, send email. Log each attempt in your analytics or tracking DB. You can build a channel priority list per notification type. For OTP, use SMS first, email as backup. For marketing emails, push notification, push first for email fallback. For receipts, email first, maybe SMS if it is important. This logic usually lives in the dispatcher layer. Bit chooses the best available channel based on user preferences, channel availability, real-time feedback from providers. Now, let's close the loop. After sending a message, we want to know what happened. This is where provider feedback APIs comes in. FCM returns success or invalid token. Twilio may return delivered, failed or blocked. SendGrid gives bounced open plate, all this data. You capture these responses and send them to an analytics or tracking service. Benefits of doing this: we can have matching and dashboards, we can have retry of fallback class triggers, and it is also easy for debugging for customer support. It's like getting receipts from your messaging system. Let's wrap this up with a really broad analogy. Retry strategy is like knocking on someone's door multiple times with increasing gaps. DLQ is writing a sticky note system. We're saying, tried everything, please look at this. Multi-channel fallback is like trying to call someone. If they don't pick up, you text them. If they fail, you email. Together, this makes your system resilient, smart, and user-friendly. A fail notification isn't dead end, it's a detour. Alright, before we wrap things up, let's talk about something every real-world system needs to handle. Latency, how fast we can send a notification. Scalability, how well our system holds up under traffic spikes. Because, let's be honest, no one wants to get their OTPs 5 minutes later or have a system crash during a Black Friday sale, right? So, latency. Latency is all about how quickly a notification reaches the user from the moment it's triggered. Let's take an OTP flow as an example. User logs in, system triggers a notification, and within 1 to 2 seconds, the user should receive a push or SMS. Here is how we keep that fast. We use queues like Kafka or RabbitMQ to buffer without blocking. Redis helps with fast lookups for deduplication and recommitting. Our notification processes are lightweight and stateless, so they scale horizontally. We integrate directly with low latency providers like FCN, APNs, or Twilio. Also, keep each step non-blocking. For example, we don't wait for feedback from APNs before moving to the next message. Now, let's talk about scalability. Imagine your app has 1,000 users today, and suddenly you go viral. You're handling 1 million users and sending 10 million notifications per day. Can your system handle that? Here is how we build for scale. Stateless services. Our processors and adapters are stateless, so we can spin up 10, 50, or 100 instances depending on the load. Horizontally, scalable queues, Kafka or SQS, they handle huge throughput with as auto-scaling. Infrastructure can scale up when needed and scale down when ideal. Sharding and partitioning. For large queues or loads, we shard the user ID or tenant ID to parallelize processing. Now let's wrap up. So in short, low latency keeps the user experience smooth and fast. High scalability keeps your system reliable during traffic spikes. Together, they make your notification system production ready and user-friendly, whether you are serving 100 users or 100 million. And that's the real goal, right? Don't forget to like, subscribe, and hit that notification bell, because even YouTube notifications have latency and retries behind the scenes.